Okay, so we can start our lecture now. Okay. Okay, so first thing about discrete random variable distribution, I will go through the Poisson distribution and hypergeometric distribution in lecture 5. And also in lecture 5, I will go through tutorial question 1, 2, 3, 4 in tutorial 2. So now we will focus on the confidence interval. For the confidence interval part, today I should finish all this part. And then next week, we will go through all the tutorial questions in tutorial 3. And then next week, because of some meetings that I cannot escape, so I can only conduct the tutorial sections on Mondays. And on Tuesday, your TA, Mr. Chen Chao, he will conduct the tutorial session. So for next week only. Next week, on Monday, I will conduct all 3 tutorial sections. And on Tuesday, Mr. Chen Chao will conduct tutorial questions. Okay? Then we can look at today, we will go through the confidence interval first. And after we introduce the concept of this, we apply it to large sample confidence interval. Then the difference between two means. So this is the key point. As far as you understand the confidence interval in large sample, then it's straightforward to extend to small sample and also in proportions. The position of this lecture in the whole part is here. In first lecture, we learned the sampling from the population to get a sample. And in the second lecture, we learned common user distribution, how to describe a population, how to describe a sample. So before that, we didn't make a distinguish between population and sample very clearly. From this lecture, I need to make this very clearly. Why? Because the goal of this lecture and the next lecture is we use the statistics in a sample to get the property of the parameters of a population. So you must distinguish these two. We need to use the X bar, the sample mean, and the standard deviation of a sample to estimate the population mean. This one we cannot. Basically, we want to estimate the population mean. So that is the goal for the next 2 lectures. So first look at the confidence interval. We know that we didn't go through the whole population. We only draw a small sample. And we want to know the property of this population from this small sample. So the question is how to estimate a population mean from a sample mean. And we already learned this. We use a point estimation. So basically, this is the population mean, and this is the sample mean. We assume that a population mean equals a sample mean. So this is the point estimation. We only get 1 data point, then we estimate it, right? And this one, they have 2 drawbacks. The first one is never exactly equal to the true value, because the sample, from sample to sample, we get the variance, right? From sample A, we get a value of a sample mean. From sample B, we get another value of a sample mean. So it is not a constant. It never exactly equals the true population. Then we have no idea about how far off point estimation from the true value, right? So we only get 1 point. So we don't know this is very close to our population mean or it's far away from our population mean. To address this question, last week we learned the central limit theorem. So if you recall the central limit theorem, this is a part of its statement. It said no matter what population it satisfies for random variable x, if we randomly choose the sample from this population, then the average of the sample, x bar, is a new random variable. So x is a random variable. X bar is another random variable. X has the population mean mu x, and x bar has the population mean mu x bar. So do pay attention, the bar on the top of x, if they have a bar, without a bar, they mean different thing. Okay, so we can use this one and give a range of our estimation. So here I just say this again and again. X bar is a random variable and it's different to x. And the confidence interval basically is just an interval that covers our level of confidence about point estimation. How? Let's look at one example. I call this is example Preston. So assume that 100 independent measurements from a large population all use the same procedure are made on the diameter of Preston. The sample mean of the measurement is 14.0. So this is x bar. And the uncertainty in this quantity is the sample mean, which is the standard deviation of the sample mean is 0.1 centimeter. The standard deviation of the sample and the standard deviation of sample mean, they are two different things. Standard deviation of a sample is S. Standard deviation of a sample mean is sigma x bar. Do you recall this figure? Do you recall this? X is here. X bar is here. So there are two different random variables. And the standard deviation of a sample mean is a sigma x bar. We get the standard deviation from this whole set of data. Standard deviation of a sample is for this part of this. So this is the variance of a sample. This is the variance of another sample. So sigma x bar and SASB, they are different, get a very different meanings. Then we can see here, we just know from the central limit theorem, we get x bar is a random variable, satisfy normal distribution, with average is mu x bar, variance is sigma x bar square. Right? So we get the distribution like this one. So this one, the center is mu x bar. And we know this figure that this is a standard unit. And the area in between only depends on the number here, not depend on the value of mu x bar and sigma x bar, right? Then we can see here is the case we know the standard deviation of sample mean. To be honest, this is a very rare case. Here, I give you this quantity just to help you understanding the concept. In the reality, this is seldom to get. So if we know the standard deviation of sample mean, for this one, we know the sample size is 100. The sample mean for the first sample is 14.0. And the standard deviation of sample mean, this is the sigma x bar. This is the sigma x bar, not a sigma x, equals 0.1. Okay? Then we can see, we know x bar satisfy normal distribution. And mu x bar, when we go to infinity sample, it should equal mu x. And then we take a point estimation here. Assume that the sample mean of the first sample equals the population mean. We get it equals 14.0. Then from the previous slide and also from the normal distribution that we learned last week, we know 95% in mu x bar plus minus 2 sigma x bar. So the range is here. We have 95 confidence that a true diameter is in the interval 13.8 to 14.2. What does this mean? You said that the point estimation is something unreliable, but you still use it. Are you kidding? No. Let's look at the next slide. So we can see, assume this is a mu x bar. It should equal mu x. No approximation here, right? Mu x bar equals mu x. And we can simplify right as mu. This is the same. And here is a sigma x bar. If we know the value of mu and sigma x bar, we can construct this distribution, this normal distribution. And it is accurate, right? And the true mean, the population mean, is just equals mu. So this is the meaning of this top part. Then we look at this part. This is the value of the first sample, x bar 1. If we put x bar 1 here, then we plus minus 2 sigma x bar, then we get this range from x bar minus 2 sigma x bar to x bar plus 2 sigma x bar. We get this confidence interval, right? So here, for this one, I divided it into two regions. One region is from this mu. This is the population mean minus 2 sigma x bar from plus minus here. And this is about 95%. If we follow this procedure, x bar can either fall into this blank middle region or this shadowed region, right? The probability it fall into this 95 region is about 95%, right? And if we follow the procedure in previous slide, we use x bar to approximate mu, and we follow that procedure, we get this confidence interval. If x bar fall into this middle blank region, is this interval cover the population mean or not? Here, I repeat it. One thing is this distribution is real. And we know the value of mu, the population mean, and the mean of your sample mean. And we also know the sigma x bar. This is the real situation. And this is our estimation. The conclusion from this one is if we follow procedure in previous slide, our confidence interval either cover the true population mean or will miss the true population mean. Only two cases, right? When our sample mean fall into this middle region, our procedure will cover the population mean. Do you agree? Which part you guys didn't get it? So basically, the difficulty of this slide is you guys don't know what's the truth and what's the assumption. Anything beyond this is the truth. This part is our procedure. The truth is the truth. We cannot change it. If we get the sample at this position, we get this interval. If we get a sample at this position, we get this interval, right? If the sample is this position, we get this interval, right? The sample fall into this region, it will cover the population mean. And the probability the sample mean fall into this region is 95%. Okay, let's look at next one. Next one is another case. If the sample mean fall into this shadow region. For into this shadow region, we follow the same procedure. We get x bar plus minus 2 sigma x bar. Then we can see this time we get a confidence interval. Does this confidence interval cover the population mean? No. It's very obvious, right? So fall into this region, cover the population mean. Fall into these two regions, not cover the population mean. The probability in the middle is 95. The probability on the rest is 95. One is 95, the other is 5, right? Okay, so conclusion is if we follow the procedure in slide 4, and we can find in the long run, 95 of the confidence interval will cover the population mean. What's the long run? Long run, that means we get one sample, do the confidence interval. We get another sample, do the confidence interval. We get another sample, confidence interval. Another CI, another CI, CI, CI. So this is called the long run. So we can see, we repeat this procedure, and you can see this one, it didn't cover the true mean. This one, it did. This one didn't, did. So in the long run, we found that 95 of this will cover the true mean. The true mean is the population mean, right? And if we didn't choose the 95, we choose the 68, then we can see a lot of cases we just miss the population mean, right? Because this interval is narrower. And if we get a larger interval, like this one, go to 3 sigma, then we can see 99.7. A lot of them cover the population mean. Only this one is on the edge. Okay? Questions? No questions? Then I get a clinical question for you. Before that, you can ask me any questions. Okay, you guys look very confident. Then we can see. So this time is a clinical question. Only guys in the room can do it. Okay, so this is a clicker question. Please use your clicker. Your smartphone doesn't work at this moment. 1 more minute. Anyone have 2 clickers? Okay, we can close the pool. So the answer is D. All the above statements are true. Statement A, B, C, all these 3 statements are true statements. The first one is the process you used will capture the true parameter. This one is just like the figure in your slide 7. In the long run, it should be 95%. This one is in your slide 6. This one just opposite of this, not opposite, the other way to say the statement B. So all the statements are true statements. Nice. We get 70% of people get it right. Okay, so in previous case, we know the standard deviation of a sample mean, sigma x bar. Then in most of the cases, actually, we don't know the standard deviation of sample mean. So we don't know the sigma x bar. So for example, let A1, A2 up to A100 is the 100 diameter of the piston. Then we can know the x bar should satisfy normal distribution. So we learned this before. And when the population satisfies a normal distribution, so this time the random variable is x. X satisfies normal distribution mu sigma square. This is x bar satisfies normal distribution mu x bar sigma x bar square. So if the population satisfies normal distribution, then we can make this approximation. This sigma is the standard deviation of a random variable x. This s is the standard deviation of a sample. We can make approximation that a standard deviation of population equals standard deviation of a sample. This is the approximation. Then we can apply this approximation here. We know sigma x bar exactly equals sigma divided by square root of n. This is exactly equal. Then we make approximation. This is standard deviation of random variable x. It approximately equals standard deviation of a sample divided by square root of n, square root of a sample size. If we know the value of a sigma x bar, we get the value of a sigma x bar directly. If we don't know, we need to make this approximation. And the approximation is not a sigma x bar equals s. This is a sigma x equals s. Okay? We can see sigma x bar approximately equals s divided by square root of n. You need to distinguish sigma x and sigma x bar. This is sigma x. This is sigma x bar. Standard deviation of a sample mean, standard deviation of a population, the standard deviation of a population for random variable x. Okay? So we use 95% confidence interval as an example. And we are not limited to 95. So we can extend to 100 times 1 minus alpha percentage confidence interval. So alpha could be any value. So we can calculate a level of 100 times 1 minus alpha percentage confidence interval for population mu sigma. How? For 95, we know it equals the x bar plus minus 2 sigma x bar. If it's for any value, what should we do? 95, this range, this area is 0.95, right? 1 minus alpha, this range will be 1 minus alpha. Then we can see this is the lower boundary, this is the upper boundary. Lower boundary is mu minus z alpha over 2 sigma x bar. Upper boundary is mu plus z alpha over 2 sigma x bar. Okay? Do you know why we need to do the tutorial question 5 in lecture 2, in tutorial 2? It's just let you practice this again and again. If you didn't get that question, it will be very difficult to understand this one. Then, basically, we can see for any value 1 minus alpha, we need to get the value of z alpha over 2. How get the value of z alpha over 2? Like tutorial question 5, like the clinical question we did last week, like a lot of things, right? So if you still have trouble to calculate this one, let me know. We can go through it step by step. So this one, we can get z alpha over 2. And I said only in a very rare case, we can know sigma x bar. In most of the case, we need to approximate, calculate sigma x bar. The approximation here is sigma x bar equals sigma divided by square root of n. We need to approximate the standard deviation of a population to a standard deviation of a sample. In this way, we can get a sigma x bar. Questions? No? Then let's go through one sample. So we can see for the filling weight of 100 bucks, the sample mean x bar is 12.05, and the standard deviation is s equals 0.1. So this standard deviation is the standard deviation of this sample. And find 85% confidence interval for the mean fill weight of the box. What's the mean fill weight of the box? So they ask the 85% confidence interval of a box filling or the average box filling. The solution is very straightforward as far as you know what they're asking. Again, here, if this is a box, and they are asked the confidence interval of x of this box, or they are asked the confidence interval of this x bar. Which one they are asking? This one, right? So we can look at the question. They said confidence interval for the mean field weight of the boxes. They are not asked the confidence interval of a field weight of one box, right? So the question is ask the filling of x bar. So then we can see we get this figure, and 1 minus alpha equals 0.85, and x bar, here we only have one sample, so x bar equals 12.05, and this is sample size, and this is standard deviation of sample. We can find 85 confidence interval, find the 85 to find 85% confidence interval. We can set 1 minus alpha equals 0.85. So this z value, this alpha over 2 is the error in this one, equals 0.075. And we can find the z value for this is 1.44. Okay? Then we can see, we can calculate sigma x bar. Sigma x bar exactly equals sigma divided by square root n. But we don't know the value of sigma. So we can approximate to the standard deviation of a sample. Plug in the value, we get this one. And this is the formula we should use. So the 85-90% confidence interval, we plug in x bar here, this alpha over 2 here, sigma x bar here, we get this range. As far as you can identify, this is ask x bar, not x. Then x bar satisfies normal distribution. And you can get the parameters of these normal distributions. Then you can get it done. And then we look at example 2. So this is example 2. Can you see it from back row? Okay. So then we can see we have 50 micro drills with an average lifetime is 12.68 and a standard deviation of 6.83. So from this sentence, we can know this sample includes 50 items, and the average of this sample is 12.68, and the standard deviation of this sample is 6.83, right? And what's the sample size? What's the sample size? 50, right? We also know that the confidence interval is from 11.09 to 14.27. For the 11.09 to 14.27, we can rewrite it as 12.68 plus minus 1.59. The reason we write it this way is that we want to compare with x bar plus minus z alpha over 2 sigma x bar directly. So we compare the confidence interval given is 12.68 plus minus 1.59 with x bar plus minus z alpha over 2 sigma x bar. We can know that x bar equals 12.68 is given here. Then z alpha over 2 sigma x bar equals 1.59. Compare these two parts, we can know this equals this, right? And the level of this confidence interval is related to this value, right? So the sigma x bar, we can know it equals sigma divided by square root of n. We don't know the value of sigma, so we approximate it to s divided by square root of n. S is 6.83, n is 50, so we get the value of 0.9645. We plug in 0.9645 here, we get z alpha over 2 times 0.9645 equals 1.59. So z alpha over 2 equals 1.59 divided by 0.9645 equals 1.65. When we get here, recall this figure. This is 1 minus alpha, this is minus z, and this is z, right? Now we know z equals 1.65. So this is 1.65, this is minus 1.65. Can you get the proportion in this in between? Can you get it? In your standard normal distribution, can you calculate the area from z equals minus 1.6 to z equals 1.65? Yes. Then we can know that this 100 times 1 minus alpha equals 0.9. So this is the 90% confidence interval. Amazing? Boring? Okay, you can take a break. We will continue it after 10 minutes break. sorry. So the concept here is difficult. It needs a pre-requirement from last lecture. If you have no clue about a normal distribution, then it will be very difficult to understand this part. So that's the reason I strongly suggest you attend the tutorial on Mondays. Then you get enough time to digest what you learn from a tutorial. If you just attend the tutorial this morning, 1 hour, just go for lunch, another half hour, you get a half hour left, no time to digest what you learn from a tutorial. So the bad part is the concept of this confidence interval and the concept of hypothesis testing is very difficult. The good side is this is a very they don't have too much variations. So even you are not very familiar with the concept, you can still get the tutorial questions done. So you just need to find the right formula. All the formulas are given. So that's the good side. Anyway, I still hope that you can understand the concept. That's the reason I spent 40 minutes to explain this to you. Okay, then we look at the example 3. For example 3, okay. So in example of a piston, so this one I didn't number the example. It's just in your slide 2. Oh, sorry, in your slide 3. In your slide 3, we assume that 100 independent measurements from a larger population. That one, that's the example of a piston. So for this one, we can know that the sample size is 100, and the x bar equals 14, and the sigma x bar, this is the standard deviation of a sample mean equals 0.1. All these three are given. So if we look at the slide 3 or slide 4, either slide, we can know the value for sample size, the average of a sample, and the standard deviation of sample. Then they ask, assume that the interval is too wide to be useful. From that example, we calculated 95 confidence interval is 13.8 to 14.2. And here they said if this interval is too wide to be useful, how to produce a 95 confidence interval within 14.0 plus minus 0.1. So what should we do? So this is the population. This is the normal distribution for x bar, and we know x bar satisfies normal distribution with the average is mu x and the variance is sigma x bar square, right? And then we know the mu x bar is 14, and this part is 13.9. This part is 14.1. Right? They want to know this part equals 95%. How? How? Does this look familiar? We just did the tutorial questions. The average diameter is 0.65, right? That's the same. We do it translate to standard normal distribution, and found this z value, right? This is z. This is minus z, right? Then we get 13.9 equals. We get minus. What's the value of minus z and z? Can you get it? Guys, wake up. Yes or no? Yes. So when you get the z value, you get a minus z equals 13.9 minus 14.0 divided by sigma x bar, right? Can you get a sigma x bar? Sigma x bar it equals sigma divided by square root of n. Okay. You guys win. You guys just use the power of silence and force me made some mistake. Okay, let's see something wrong. No. We get this. Because sigma x bar equals 0.1. Okay, so this equals 0.1. So we get this. Okay, even simpler. This is 1.96. We get this equals 0.1. So it equals sigma divided square root of n. Oh, okay. Okay, this part. Okay, we get the z. This is the minus this. So we get okay. 0.1, 0.1. Six minus 1.6. This is the x bar. Satisfy this. This is the standard normal distribution. This is the Okay, so sorry. So this is the X bar 100. Okay, sorry. So this one is more complex than I think. Sorry. So first, this is the normal distribution for X bar, and this X bar comes from 100 items. So we can see the confidence interval is from 13.8 to 14.2. This is the original one, and we know the area is about 90% from 13.8 to 14.2, right? So for this random variable X bar 100, we can know it satisfies a normal distribution mu X bar 100 and sigma X bar 100. Here, I need to distinguish the random variable sample mean from 100 items and the random variable sample mean from n items. Because these two are two different random variables. One is the average of 100 items. The other is the average of n items. And for this one, they want to get the narrower confidence interval, but the narrower distribution, plus minus 1, from 13.9 to 14.1, but still the confidence interval is same, is 95. Sound something weird, right? The reason is in this distribution, we get a sigma X bar 100. In this one, the distribution is sigma X bar n. This sigma bar X 100 equals sigma divided by square root of n. And this time, the value of n is 100, right? And in this distribution, the sigma X bar n equals sigma divided by square root of n. What is the value of n here? This is the unknown, right? We want to get this value. And we can see this value, sigma X bar 100, we know it equals 0.1. From this part, from the slide 3 or slide 4, we can get this. So that's sigma X bar 100, it equals 0.1. So we can get the value of sigma, right? So this square root of 100 is 10. This is 0.1. From this equation, we can get a sigma equals 1. This sigma is the population of X. X satisfies some population, and the standard deviation of this x is 1. And we can plug in here, we get sigma x bar n equals 1 over square root of n. Is this clear? And we know that here 14.1 corresponding to the standard normal distribution z equals 1.69. This is the standard normal distribution. So we can know 14.1 minus 14.0 divided by sigma x bar n equals 1.96, right? So we can get sigma x bar n equals 0.1 divided by 1.96. And this part we get 0.1 over 1.96 equals 1 over square root of n. Did you get it? This part is similar to the question part C in question 5, tutorial 2. We know in this normal distribution, the range and 95%. So we want to get the variance in this normal distribution. And the variance of this normal distribution related to the sample size. We need to get the value of sigma from this one. This is given. So we get the value of sigma from this one and the value of sigma x bar n from this two. Here involves 3 random variables. Okay, I hope that half of people get it. We need to move on, otherwise I need lecture 6. My laser pointer. Okay, so in previous examples, we always focus on the two-sided confidence interval. That means we need a two boundary, lower boundary and upper boundary, and they are symmetric relative to its average. The distance from upper boundary to the average, the distance from the lower boundary to its average, they are equal to each other. Then we get the one-sided confidence interval. For the one-sided confidence interval, we get basically, we don't care about two-sided, we only care about one side. So if this is the lower boundary, we just care about if the population larger than this certain value. And if we get the upper boundary, we just get the opposite, is from minus infinity up to certain value. And this part is closely related to the hypothesis testing, and I will skip this part. Then we get one extension. So far, we just focus on the random variable of a sample mean. If we get two populations, and the difference between two populations is another random variable. So we can see we get one sample from a population with the average mu x and sigma x. Another sample is from mu y and sigma y. So this time we get the two populations, and we want to know the difference between two populations. So in this case, we get a random variable either x minus y or y minus x. We get a new random variable, linear function of two random variables. So this is a new random variable, x bar minus y bar. So we get this is x bar minus y bar. We can use the linear function of a random variable to calculate this. If you are interested in this, you can do it after the class, and it will not be tested. So this one will given directly. So if you really want to know how it comes, we can go through it later on. So here we need two standard deviations. One is standard deviation of population 1. This is the standard deviation of population 2. We get sigma x approximately to this sample from the population x. This is the sample standard deviation from population y. Basically, the concept is the same. It just changes the random variable from x bar to x bar minus y bar. This just challenge yourself. If you don't believe me and you think this is wrong, you can try to prove it. Anyone interested in this? Okay, we skip it. So this one basically is just very straightforward. You know this is the difference between two populations, and you just need to use this formula, plug in. So basically we get the sample A, sample B, then plug in the formula, get the results. So all your tutorial questions and your final year exams, the final exams is just similar like this. So you just need to find the right formula, plug in. So don't get scared. Now I need to distribute something. Do you have a table with you? So please do your tutorial questions. Otherwise, I cannot explain it further. You can see we need this again and again. The normal distribution will come out on the hypothesis testing. Okay. For the small sample, basically we just replace z value by t value. That's all. So we can see if we get a small sample, in previous examples, we always said we need a large sample. The sample size is larger than 30. But sample size larger than 30 sometimes is very time-consuming and need a lot of money. So if we get a small sample, definitely we will save some time. So for the small sample, we replace this. You can see this sound familiar, right? If I replace S by sigma, what's this? I replace sigma S by sigma. What's sigma divided by square root of n? Sigma x bar, right? So this is very similar. So this quantity has a Student's t distribution with n minus 1 degree of freedom. So if you have 5 items, the degree of freedom will be 4. If you have 3 items, the degree of freedom will be 2. If you have 10 items, the degree of freedom will be 9. Okay? So when the sample size is large, the distribution of above quantity is very close to the normal. So we can see this one is T1. 1 is n minus 1. So that means we include 2 items in each sample. It gets this dashed line. Then this is 5 items. This is 11 items. And this solid pink line is for z value. So we can see when we increase the sample size, it will approach to z value. Then we look at the small sample confidence interval. I said that we need to replace z value by t value. So this is a sample of a t table, part of a t table. We can see the first volume, the first column. First column is the degree of freedom, nu. So this degree of freedom equals 1. When the degree of freedom equals 1, how many items do we have? 2, right? So the degree of freedom is n minus 1. So we need to identify what's the degree of freedom. Then we look at the value here. And the value in this table is the value of t. The value in this table is the value of t. This is different to z value, z table. For the z table, the inside of the table is the cumulative function up to z, right? And here, this is the value of t. And look at this line. This line is the value of alpha. How we define alpha? Alpha is here. So the area from t equals t to infinity. This is the cumulative function of t. And this shadowed area is 1, the whole thing, minus the cumulative function of this. So this is the value of alpha. This is the value of t. Then we can see for this one, when t equals 3.365, we know this area is 0.01. When the degree of freedom is 5. When t equals 4.0, this area is 0.005. How about t equals 3.8? Something in between. What should we do? If the t value fall into between, we just report 2 boundary values. If t equals 3.8, when degree of freedom is 5, we need to report that the area is larger than this, smaller than this. For the z table, you just take either one. For the t table, you need to report 2 boundaries. Okay? The degree of freedom, I repeat it a lot of times. This shadow area is 1 minus its cumulative distribution function. The symmetry is just this is about 0. So if we get a t here, and here we get minus t, what's the area from minus infinity up to minus t compared to the area from t to positive infinity? the question is, if we get minus d here, and we can get the shadow area here, what's the relation between this shadow area with this one? Same, because by symmetry, this is symmetric of around t equals 0, right? So when we flip it, this should be same area. Okay? Another clicker questions? So this question is about a t-score. So the question is, the t-distribution has what degree of freedom when the sample size is n? This one is the easy one. Okay, one more minute. No change. Okay, we can close it. I think I can close it now. Yeah. Oh? Anything wrong here? It should be n minus 1. So do remember the degree of freedom is n minus 1. N is the sample size. When we look at this one, the random sample of size 10 is to be drawn from a normal distribution with mean 4. The student t, statistics t equals this, is computed. What's the probability that t larger than 1.833? So we can see the sample size is 10, x bar is 4. So sample size is 10, so we know this is the degree of freedom is 9. And from the t table, we look at 9. When it equals 1.833, it's here, right? So we know this area is 0.05. So this is the probability t larger than 1.833 equals 0.05. Okay? Then we can see we extend it to side, we render two-sided. This you can see, this is Tn minus 1. So this is the degree of freedom. For the two-sided confidence interval, this is alpha over 2. For the one-sided, this is alpha. So this is similar to the large sample. We get a Z alpha over 2 for two-sided and a Z alpha for one-sided. And if we don't know the sigma value, we use this student T. But if we know the value of sigma, this sigma is the standard deviation of the population. If somehow we know this value, we should use a Z table instead of a T table. If we know this value, even it's a small sample, we should use the Z table instead of a T table. Then we can extend it to the difference between two populations. One case is this two, the sigma x. These two populations has the same standard, has a different standard deviation. Then we get this set of formula, and this is the degree of freedom. You can calculate based on that. Then you look at the T table. Do remember, find the right line to get the degree of freedom, and use this formula. All this formula will be given, and you don't need to memorize it. The challenging part is how you can judge the two populations have the different or have the same standard deviation. If they are different, you use this set of formula. And if they are same, you use this set of formula. The example that I skipped, example 6, is very straightforward. You just need to plug in the values. And then I use the rest of the time go through the confidence interval for proportion. The key is still in the first 10 slides, the large sample. As far as you understand the large sample, you can get all the rest. Nothing changed. Just replace Z by T. And for the proportion, we can see here we defined P wiggle. Do you remember we defined P hat before? P hat. Do you remember this in the binomial distribution? And that equals x divided by n. And here, this is P wiggle. For one population, this is x plus 2 divided by n wiggle. And n wiggle equals n plus 4. And this set of formula doesn't have solid mathematical background basis. This is just based on experience. That's the reason somehow you can get the lower limit less than 0. In reality, can we get a probability less than 0? Can we? No. The probability is always from 0 to 1. If something smaller than 0, larger than 1, that means something wrong. So if it's smaller than 0, replace it with 0. If it's larger than 1, replace it by 1. This is just an empirical formula. People found if we use this set of formula, then we get a better estimation. And no reason plus 2, no reason plus 1, no reason plus 3. We just try all the numbers, found this one is the best. And for the one-sided, you use this set of formula, replace the alpha over 2 by the alpha. And this example basically plug in formula. And here I need to see the difference between two proportions. And here, the P wiggle x equals x plus 1. Not x plus 2 anymore. It's x plus 1 divided by n wiggle x. And n wiggle x this time equals nx plus 2, not nx plus 4, nx plus 2. Again, because this set of formula are from experience, not from a mathematical derivative. So just based on the experience, this set of formula will give you a better estimation. Again, whenever the lower limit is smaller than -1, because we use one random variable minus the other random variable, both of them is 0 to 1. So if it's one minus another, then the range will be from -1 to 1. The lower limit is less than -1, then replace it by -1. If the upper limit is greater than 1, then replace it by this. Okay, I fly through the small sample and the proportion. The small sample is very similar to large sample. We just replace the z in large sample to t in small sample. Then we replace z table by t table. For the proportion, basically it's empirical formulas. So all these formulas are given. You don't need to memorize it, but you need to know when we apply this formula. And I will go through this in tutorial questions by more details. Today, my major goal is to hope that you understand the confidence interval of a large sample in one population. So that's my goal. Hope I'm not that disappointed. Okay? Any questions? If not, that's all for today. And for next week, I can only conduct a tutorial on Mondays. On Tuesday, we still have a tutorial section, but it will conducted by my student, Mr. Chen Chao. Okay? Thank you for coming. Oh, one more thing. Sorry. About a group project, I forgot this. I put it in lecture 2. Sorry. So for group project, basically the group size is 4 people, and you need to form a group by yourself before this weekend. Is it too rush? Do you need more time? Okay, plus 1 more week. Okay, then here I will change it to plus 1 more week. Decide your group project before this, and after you form your group and decide your group project, then put it. You need to key in this by yourself. Just this is in key information lecture 0, so you just key this. And do you think this is too rush or not? Oh, okay. Okay, too rush 1 more week. Because I should give you this presentation last week, but somehow we get technical problems. I didn't go through it. So for the group project, and it's contact your TA, Mr. Chen Chao, and this is his email address. And for the topics, basically it could be anything. You need to think about these 3 questions. What's your random variable? Must be clear about your random variable. Are there any survey results available on your topic? If they are available, then you compare your survey result with the available result. If not, you need to divide your survey into 2 groups, then compare difference between 2 groups. And how much time do you need to spend? This one, basically, I hope this project, you can finish it in 2 hours in total. In 2 hours. If more than 2 hours, let me know. That means you something wrong. So this I just target 2 hours for your people. Don't spend 20 hours, just 2 hours. Then you are strongly encouraged to discuss your topic with me before you start your project. And for this project, I'm on your side. Do use this powerful resource. Okay? Then, for the content of the report, it includes introduction, why you choose this topic, summary statistics, basically just a box plot or histogram, and the confidence interval. Just need to calculate one confidence interval. That's enough. Don't need to calculate 3, 5, certain. Some people even calculate 5 confidence interval. Not necessary. One is enough. At most 2. Hypothesis test. If you have a result, you have other survey result, compare your result with existing result. Otherwise, you need to divide your survey questions into 2 groups. For example, how about boys, how about girls? Then you can compare the difference between this, then conclusion. And for appendix, no page limit, you need to put your sampling detail, summary question, original data, detailed calculations, and reference if available. Don't need to take pictures. I will upload it to NTU Learn. Okay, that's all. Sorry.